Oh, so somebody asked me, does anyone know where the lectures are posted? It's under pages in Canvas, and then there should be a link to it. Okay, so I'm going to do probably like a little mini mechanism for each of these. If this was an actual exam, you would just need to draw the product. But assuming this is like a draw the products page. So let's get started with this. First one here, we've got Br2. So our double bond can attack one of these bromines. I'm going to draw going straight to the cyclization. We make something like this. From this point, our other Br can come in. It's going to attack at the more substituted center, doing an SN2. Giving us an anti-product. And you guys covered these reactions last semester, right? Okay. Second one here, this is a reduction, really simple. You're adding H2 to everything. You're just going to get single bonds. This one down here, we're in peroxide. So HBr would normally add to our more substituted carbon. Looking at this, we have a tertiary and a secondary position here. It would normally add to the tertiary position, but because we're in peroxide, it's going to add to the less substituted. So it should give us this bromination product. Our next one here is really similar to this one, except we have water. So our first step, we're going to form that bromonium ion. And then water can come in. Do an SN2 at our more substituted center. And we'll get anti-addition of water and bromine. This is kind of the opposite of this problem here. So we'd pick up a proton, generate the carbocation on our tertiary position. Br can then come in and brominate. Our last one is going to be a rearrangement. So you can pick up a proton, we have a secondary center that's next to a quaternary center. This can do a methyl shift. Leaving us with a tertiary center, so we went uphill in terms of stability. So this is a more stable center, water that can then come in. And give us an alcohol. Any questions on these? Everyone looks really excited. Okay. So we're going to do chapter 9 today. We'll probably get through all of it. Chapter 9 is very similar to chapter 8. It's alkynes. the reactions are almost identical. You're just going to do most of them twice. So for naming alkynes, if I had a 3-membered chain, this is propane. For a double bond, so we have the suffix ane here. This is a propene. Our suffix is ene, and then for a triple bond, gonna be propyne, yne. Did you guys go through chapter 9 last semester? Kind of. Okay. So in case you guys have forgotten, so because these are linear, I'm gonna actually draw out what this looks like. Sometimes these get a little confusing because you don't have like a bend in your chain, and it just kind of looks like, especially when you draw something like this here, this equates to a CH3, C, triple bond, C, CH3. So something to watch out for. It isn't just like a really long bond with an awkward short triple bond in there. These are linear, so they're going to look a little bit different. For naming these, our propyne is going to be our highest priority. So if we have something that has both a double bond and a triple bond on it, like this here, for counting our longest chain, although we don't really get a choice between the two of them, we would go through our triple bond first. So let's actually do one that's a little different. So this one here, this actually makes us choose. So there are 2 different options for counting. If we counted left to right, this would be 1, 2, 3, 4, 5, 6 here. Right to left, 1, 2, 3, 4, 5, 6. We are going to favor our triple bond, so we are going to go with this top here because this gives us the triple bond on 1 versus the triple bond on 5 here. This is an E alkene because it's trans. It starts on 4. So for naming this, we have 1, 2, 3, 4, 5, 6. We have both a double bond and a triple bond, so this would be a 4E hex, 4-ene 1 ine. When you have both of them, you kind of just shove them together and put both of them in there. You're probably not going to see a ton of these that have both of them on there, but just so you know. Okay, so moving on to a more complicated example of these. Okay. Okay, taking a look at this molecule here, we can either go left to right, right to left. It's going to be easier to, or it's going to give us a lower number on our triple bond to go right to left here. So I'm going to number these out. 1, 2, 3, 4, 5, 6. We have 6 carbons, so this is a hexyne. Our triple bond is on 2. Let's see. So we have methyl group on 4, so it's a 4-methyl. We have a chloro on 4. We have a chloro on 5. Doing R and S. We've got, starting with this one on 4 first, so Cl, carbon, carbon, carbon here. So the Cl is going to be our highest priority. Taking a look at our 3 carbons, this is carbon bonded to chlorine. This is carbon that's bonded to 2 other carbons, CH3 by itself. So this would be 2. This would be 3 here. This is going clockwise, so this one should be R. Gonna redraw real quick for the other one. Okay, taking a look at our second stereocenter here. Same thing, Cl is our highest priority. Carbon with a lot of stuff on it, carbon by itself. So 2, 3. This is also clockwise. This is also R. Putting it all together, we have a 4R, because this Cl was on 4, 5R. Going alphabetical, so we have 2 chloros here, 4, 5, dichloro, another methyl on 4, and then 2 hexyne. Any questions on this naming? Should be pretty similar to the alkene. Honestly, it's a little easier because you don't have to do E and Z for these ones. Okay, I'm gonna get into some reactions. To make a triple bond, it's pretty straightforward. So someone had a question in the chat. Oh yeah, someone asked if you can also say hex 2-ine, and they're both fine. Either way works for that last part of it. Okay, so reactions that make double bonds. You have Br, you throw in base. You can do an elimination. To make a triple bond, you are essentially going to do the exact same thing. So there's really 2 different options. They can either be on the same carbon. So if we throw in something like NaNH2, you'll originally make this through some sort of elimination. So we can pull off a proton to make an alkene here. But we also can do this again. So NaNH2, can pull this off, and then we can get to a triple bond. The other way you can do this is if your BRs are on other sides of the molecule. So by having these bromines on here, these are going to be a lot more electrophilic than these ones that don't have any bromines on them. So because of that, it's actually going to selectively make triple bonds. So if I throw in NaNH2, this is going to want to take off this proton here, kick out this Vr. We're going to end up in the exact same spot we were up here. So then another equivalent. Can come in, pull off this proton, and get us our triple bond. So this is useful because if you're starting here, you can actually make a triple bond pretty quickly out of this. So we'll do kind of like a little mini synthesis of a triple bond. So if I take Br here, throw in NaNH2, we can make a double bond. In order to make a triple bond, we're going to need 2 leaving groups. And our best way to make 2 leaving groups is going to be to throw in either Br2 or Cl2. So if we throw in this Br2, we now have exactly what we had over here. We can throw in excess NaNH2. And make a triple bond. Also, this is my shorthand for excess. I just put XS on there. So if you ever see that, that just means more than one equivalent. So someone asked me for this, do you actually need 2 moles of base? And this is a little bit of an interesting question. So this is a pretty, if you were to try to do this with 1 mole, you're not gonna, so I'll say 1 equivalent. It's gonna be a little bit of a mess. So you'd originally make, you're really gonna get 3 products. You're gonna get some combination of these 3. So when you make one of these, this can then react with this. So you're probably going to end up with like somewhere between a third of all 3 of these, because you're going to run out of this after a while. Actually, I think you end up with like 25%, 50%, and 25%, something like that. So this is not a great way of making this here. We'll talk about a way to make that in a bit, but 1 equivalent really isn't a thing for this material here. You always pretty much need to add 2 equivalents because you're just going to get a giant mixture. So I'm going to talk about how to make this in a second. First, I'm going to talk about some reductions because these are pretty straightforward. So if I throw in H2, I'm going to make this. Something I don't know if you guys learned before is that it actually adds them syn to each other. So I'm going to put like a little star on these ones. So if I was to add H2 across this, what I'm going to get is draw them in a different color. Not that the colors come off that well. This, where both of your H's are adding to the same side. When you're like dealing with something that's on a metal surface, you kind of have like these H's that are sticking up. So when it comes in and attacks, it has to attack both sides of the plane, and you end up adding them syn to each other. This is going to be important for triple bonds. So for reducing a triple bond, if you throw in H2 and palladium on carbon, what you're actually going to get is just a single bond. So at some point in time, you would get this, but this is really easy to reduce comparatively. So someone asked, what does the PDC mean? It's a reagent called palladium on carbon. It's a metal carbon complex. You guys don't really need to know, but essentially it like lets you make a sheet of a metal so that you're able to attach hydrogens to it. You can also use platinum. I think maybe you guys did that one also. They're the same reaction. Okay, so this here is really easy to reduce. So the second that you make this is going to happen. H2 is a gas, which makes it very difficult to get one equivalent of. You essentially have to flood it with as much of it as you possibly can have, because that's how it's like hard to measure out a gas in a container. So when you're dealing with H2, if you put it into solution with an alkene, it's going to give you an alkane. So what you have to do is you're going to add something that's called a poison catalyst. And the one we use is called Lindlar's catalyst. So if you were to add an H2 and essentially what this is going to do is it's going to stop your reaction at the halfway point. So if we have something larger, and like I said, you add them to the same face. So when you add in this H2 and Lindlar's catalyst, you're going to end up getting a cis double bond. So in terms of reductions, this is our way of making a cis bond. If we want to make a trans double bond, we need to use a different reagent. And that is one I'm actually going to go through the mechanism for. So I'm just going to redraw this real quick. Make it a little smaller. H2, Lindlar's catalyst. for creating a trans double bond, we are going to add in sodium 0 and liquid ammonia. And what that's going to give us is this here. So how this works is sodium 0, we usually think of sodium as being Na+. Na by itself, which is like the stuff that you can buy and like throw in water and it'll explode, is sodium with a single electron, or so sodium radical. And what this can do is it can donate this one radical, because it wants to be Na+, into your triple bond. And that is going to split this triple bond. You're going to have one electron move over to join it. The other one is going to get kicked to the other side of it. And we're going to make what looks like this here. So we have a negative and a radical. We originally just had one bond, which was made of 2 electrons. We added this extra one in. Now we have 3. So there'll be one over here, one down here. This can pick up a proton from our ammonia. Maybe not. Oh, sorry. We're going to get basically half of the product we want. From this point, another sodium can give us another radical. We can pick up a second proton. And we'll form a product here. So to kind of review, 3 different reductions you can do. Just throwing in H2. So this is one that you need to know the mechanism for. Someone asked in the chat. If I go through a mechanism, I would recommend knowing it. That means it's free game on your guys' exams. You'll have some sort of mechanism question at some point. H2 and Lin-Lars. Gets you to your cis double bond, and then sodium NH3 allows you to make a trans double bond. So some similar reactions to some really similar ones to the one from chapter 8. So if we throw in HBr with a double bond here, we can brominate. Same thing with a triple bond. If you throw in HBr, if you put one equivalent in solution, you can make this single brominated product, and then throw in another equivalent. You can brominate twice. Same thing with HCl. this reaction should be really straightforward. It should make a lot of sense. Same thing with like peroxide. So HBr and peroxide. Gets us to here, triple bond, HBr and peroxide. Adds an anti-Markovnikov, and we can do the same thing. Let's just dibrominate. And let's do the BR2 one, because that one's really easy also. BR2, essentially the same. I'll save those ones for Monday. Yeah, let's do double one first. So if I add BR2 to a double bond, we can get an anti-addition. If you add it to a triple bond, you can also get an anti-addition. Also note that these guys are on opposite sides. They're still like anti to each other. Second equivalent is going to kind of ruin that because you're going to end up with 4 bromines on there. Essentially, all the rules that applied to alkenes also apply to alkynes. Okay, I'm going to go through, I guess, 2 more hydrohalidination. Someone asked if for the last one if you need access to react all the way. So yes, this one is one where you would need access if you wanted to go from here to here. Probably covering what everyone can see. So 2 equivalents to get to here. You just add a 1 equivalent. And someone asked if there are recommended problems to review these. And yes, I'm going to post a worksheet on them and also give you guys some book problems at some point. There's like on the files, there's like a recommended book problems, and I'm just going to keep updating that file when I add in new chapters. So I won't actually post a new one for that, but for like the problem sets, you should see it. If you see a new problem set, expect that you should like reopen that file and find more book problems to do. Okay, so the last 2 are for adding oxygens. If I add in BH3 and THF, as what? No, wait, that's the wrong one. I don't want to do that one first. Let's add in H2SO4. And water, which is basically just H3O plus. We can generate 1 bond to oxygen here. If we do the same thing, or at least very similar with an alkene, so we're going to add in H2SO4, H2O, HgSO4, which is just a catalyst. You don't need to worry about the mechanism for this one, at least for a part of it. What this is going to end up giving us is, so it's a similar concept. It's 2 bonds to oxygen, just like you make like extra bonds to bromine. It just happens to be on the same oxygen. So here you had just a single bond to this oxygen. Now we're going to make a double bond to oxygen. The way that this works is it's going to go, the first part of it is exactly the same for the most part. We are originally going to make this. From here, we are in acid because we're in H2SO4. So we're going to do what's called an acid catalyzed atomerization. Which is a really fancy word for a proton shift. Essentially what's going to happen, our lone pair from this oxygen comes down. We're going to pick up a proton here. This is going to make our alkene, or sorry, our carbonyl. And then whatever our source was, I'm just going to have water, can come in, grab this H, and you make a ketone here. So the overall reaction is pretty simple. H2SO4, H2O, HG, SO4 gets you to a ketone, H2SO4, and water would get you to an alcohol here. Following the same principles, you're adding, as everything else, you're adding an extra bond to oxygen. In this case, it happens to be to the same oxygen here. The last one I'm going to do is the anti-Markovnikov version of this. So BH3, THF, NaOH, and peroxide. Gets us to here. If we use the exact same reagents on a triple bond, we're going to make an aldehyde. So we're going to form two bonds to an oxygen. It's going to be on the same oxygen. It's going to be on our anti-Markovnikov position. You might see, what do they like to do? So instead of BH3 THF, sometimes they have R3B THF or 9BBN. These are reagents your book likes to throw in. They all mean the same thing. Oops, not a 2 there. Should be a 1 also. The second step will be the same. So I'll put the 2 in there. So it should still be NaOH, H2O2. These are all reagents that do the exact same reaction. Okay, so this first part operates the exact same way as it does in an alkene. So we're not going to go through it, and you guys, because we learned it in chapter 8, which was technically last semester. You guys aren't responsible for that part of it, but the catalyzed part you are. So BH3, THF, NaOH, H2O2 gets us initially to here. We are going to do, so we're in NaOH. This is a base. So we are going to do the opposite reaction of what we did before. We're going to do a base catalyzed isomerization. So what that's going to be is we are going to pull off this proton here. Generate our aldehyde with a negative charge. It can then pick up that exact same proton and get us our aldehyde product. So all of these reactions are pretty similar to what you see in chapter 8. H3O plus gets us to an alcohol. Oops, I need to roll on. For a triple bond, that's going to get us to a ketone. Our BH3, THF, NaOH, peroxide gets us to this terminal alcohol, and then keep going. So let's say 9 bbn, NaOH, H2O2 gets us to an aldehyde here. Oh, so one last thing. For this one here, if you have something that looks like this, and it applies for either of these technically. There is not like for this one here, there's a terminal one and a primary one and a secondary one, so it's going to form on this secondary center. For this one here, there's not really any selectivity between the two of them, so you can make 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. Either this ketone or this ketone, it's not going to be selective for either of them because these are essentially the same in solution. There's no reason why you would pick one of them over the other. It's not like a Markovnikov point here. And technically the same thing with this one. If you use this reagent, you would also get the same products there. Okay, so that is most of chapter 9. We're going to go through the last parts of it at the beginning of Monday and then talk a little bit about radicals, which I think you guys also kind of touched on last term. So I will see you guys then. Oh, for office hours today, it'll probably be like 1 to 3 instead of noon to 2 because I have to go do my saliva test.